In this lecture, we are going to look more in depth at how one describes a portfolio mathematically. Basically, this is going to consist of a few definitions and some statistics. As you'll see, this will be necessary to optimize a portfolio, which is the goal of this section. Okay, so as you know, a portfolio is a set of weights, which tells us the proportion of each asset in our portfolio. For example, let's suppose we have Apple, Google, Starbucks, and IBM stock under consideration. Let's also suppose that we have $10,000 to invest. Let's say we decided to use $2,500 to purchase Apple stock, $5,000 to purchase Google stock, $1,500 to purchase Starbucks stock, and $1,000 to purchase IBM stock. In this case, our corresponding weights would be 0.25, 0.5, 0.15, and 0.1. In general, our weights are described by a vector W. W sub I tells us the proportion of our money we've invested in asset I. In this class, we'll say that I goes from 1 up to D. This means that we have D assets in our portfolio. Note that we have a constraint on W. Since the vector W contains percentages, it must be the case that the sum of all the W's is 1. Sometimes we have an additional constraint that each W sub I must be greater than or equal to 0. In fact, this constraint is quite common. Now you might ask, how can W sub I possibly be less than 0? How can we have a negative percentage invested in an asset? This is a case that we call short selling. We'll discuss this more later in the course, but for now, it suffices to understand that a negative weight corresponds to short selling. It essentially means that you are selling an asset which you do not own and then buying it back at a later date. Your hope is that the asset will go down in price so that you can buy it back for less than what you sold it for originally. Note that this is the opposite of what you want with an asset that you would actually buy. If you actually buy a stock, you want it to go up in price so that you can sell it at a later date for more than what you bought it for. In either case, whether you allow negative weights or not, it still must be that the sum of the weights should be 1. Okay, so what's next? At this level, portfolio theory is concerned with the returns over a single period. We'll call the return on asset I in this period R sub I. As you know, this return is a random variable. Therefore, it has a distribution, it has a mean, it has a variance, and so on. The mean of return R sub I is just the expected value of R sub I. We use the symbol mu sub I to denote the mean, as we usually do. Note that if we combine all the mu sub i's into a single vector called mu, this is a D-length vector. Now, since we have multiple assets, we aren't just concerned with the variance of each R sub I. Remember that it's possible for different assets to be correlated. Thus, a full characterization of the second-order statistics would require the covariance matrix. We'll call the covariance matrix capital sigma. Each element in sigma ij is equal to the expected value of R sub I minus mu sub I times R sub j minus mu sub j. As you know, this is the covariance between asset I and asset j. If I is equal to j, this is just a variance of asset I. And as expected, sigma is a D by D matrix. Okay, so what's the next step? So far, we've looked at the weights which describe a portfolio, the return on each asset, the expected return on each asset, and the covariance matrix. The two key statistics we are concerned with in portfolio optimization are the expected return of the portfolio and the variance of the portfolio return. We'll call this mu sub p and sigma sub p squared. To understand how we might calculate these, let's start with the simplest case where we only have two assets to consider. In this case, we only need a single weight to describe the portfolio. The other weight can just be 1 minus the first weight. Okay, so in this case, what is the return of the portfolio? the return of the portfolio, let's call that R sub P, is equal to W times R1 plus 1 minus W times R2. Let's make sure that this makes sense. Let's suppose that asset 1 returns 20% and asset 2 returns 10%. Let's suppose that I invest 100% of my money into asset 1. In this case, my return should be 20%, since that's exactly the same as investing directly into asset 1. You can verify that the same thing happens if I invest everything into asset 2. What if I invest 50% into asset 1 and 50% into asset 2? In this case, I get 0.5 times 20% plus 0.5 times 10%, which is equal to 15%. So it's a mixture of the return of the two assets. Hopefully that makes sense. Let's recognize that R sub P is a function of random variables, since R1 and R2 are random variables. This means that R sub P is also a random variable. As discussed previously, we know that this therefore has a distribution, which we can talk about in terms of its mean and its variance. What is the mean of R sub P? Well, that's just the expected value of R sub P. If we take the expected value of both sides, what happens? Firstly, we can split up the addition since the expectation is a linear operator. Second, we can pull out the w's since they are not random variables. Thus, the mean of RP is just the weighted sum of the expected return on each asset. Okay, what about the variance of RP? This one is a little more tricky. It is not just the sum of the individual variances, because remember that R1 and R2 could be correlated. The best way to figure this out is to start with the definition of variance. As you recall, the variance of RP is equal to the expected value of RP minus mu P all squared. If we plug in what we know for RP and mu P, we just get the weighted sum of R1 and R2 and the weighted sum of mu1 and mu2. The trick is to group together everything with the coefficient W and everything with the coefficient 1 minus W. Once we do that, we can expand out the square to get three different terms. The first term has the W term squared. The second term has the 1 minus W term squared. And the third term has 2 times each of the terms multiplied by each other. We recognize that each of these three terms are quantities that we already know. They are the variance of R1, the variance of R2, and the covariance between R1 and R2. Note that one alternative way to write this is in terms of the correlation rather than the covariance. As you recall, the correlation is equal to the covariance divided by sigma 1 and sigma 2. This may be useful later, since we like to think of how related two assets are by their correlation rather than their covariance. So be aware that we may use either of these formulas to calculate the portfolio variance. There is one useful fact that we can see from our expression for the variance of a two-asset portfolio. As you saw previously, when we create a portfolio from completely independent assets, we reduce our variance. But this is now the case where R1 and R2 may not be independent. What happens if W is a positive number less than 1? In this case, 1 minus W is also positive, and therefore W times 1 minus W is also positive. If R1 and R2 are positively correlated, then the entire third term contains only positive numbers. Therefore, this increases the variance of the portfolio. What happens when R1 and R2 are negatively correlated? In this case, we decrease the variance of the portfolio. As an exercise, you may want to consider what would happen if sigma 1 is equal to sigma 2 and we have perfect correlation. That is, rho is equal to 1. In this case, does splitting your investment between asset 1 and asset 2 help you reduce risk? Give that a try and I'll see you in the next lecture.